So we're not going to talk about only much today, but it is something we use Solaris for a lot. So it's coming back, even though I should probably stop now and let it go after a few years, but it's still my heart project. Sorry. So I'm Chris from Megalis, and so just to tell you very briefly about Megalis, it was created by some artists with coming from various backgrounds, like essentially FX actually, but from small, big companies, and we wanted to be here in Japan and do what we like to do while being in a country we like to be in. That's as simple as this. We made a studio in 2017, and Houdini was our core software from day one. We started doing FX essentially, since that's what we were better at. And now we do whatever is necessary for production, including concept, storyboard, until compositing. So when we got in particular the Oni project, we started to handle every type of things. And so at that time, it felt absolutely necessary to do something a bit drastical to our pipeline. And so using USD and Solaris was, at the time, what made sense, even though at that time it was still a little bit early, maybe. But we did the full production in 18.5. So it was already great. And so 2,200 shots, using Arnold at the time for render engine. And since then, I wrote 8 other projects, removing the very small ones, but that's, we've been using constantly without problem and constantly trying to upgrade whatever we made at the time. And this is exactly what I'm going to talk about first. So basically 4.5 years of Solaris, or so. And we went through quite a few things. One thing that, happened is, so as I said, we updated it pretty early. And at that time, you cannot really see other talk about it. You can essentially see how to use Solaris and what you can do, but you cannot really see so much what's the nicest way to use new USD and in a production, how we can go into this 2,000 shots and thousands of assets production without regretting back, and thinking, oh my God, why we don't do it this way? It's too late now. So we had the support of side effects, which was really great. We were chatting and we built something. The way we built it, and actually I'm just going to simply probably read a bit through these points. So as I say, it was an early adoption. We use Solaris rather than using USD. And what that means is that we used USD, essentially we exported our asset as USD. We exported the group of the modeling, the texture, and the look dive information as USD. But overall, we were not using USD so deeply at the time. However, obviously, being inside Solaris and whatever Solaris is outputting and how it's being rendered, of course, it's manipulating USD. But us, ourselves, not so much, actually. And so, of course, our assets were all in USD, and it was really convenient to give it to another company, which was great. But we didn't make it the very initial source of our files, which is what I'm going to talk a little bit more after about. So, as I mentioned, it was our first time to to make plenty of assets, 1,000, 100, whatever. From a company that does 0 asset, you can imagine it's a starting step, especially with 15 people. So, at that stage, even the simplest implementation already changed everything to us. We, used USD for assets, but any other cache were in ABC or BGO. One big reason is because in 2020, whatever was supporting USD, was very minimal. And so if you start exporting everything in USD and you want to do something else, the other software don't support USD. So at that time, and for a while, we decided, okay, we're going to keep working with ABC. We're going to reference our ABC, and then, ABC is Alembic. And we're going to keep working on that until the day we decide to fully commit to export USD file. The scene assembly was happening inside the Houdini file, which I'm going to show. And again, at the time, it's because you start with nothing. You want to have the ability to debug, to control, rather than just assuming everything is going to be correct and that you can hide to the user absolutely everything. And you're going to see about that more. So using all this HDA inside the graph, it's obviously slower than if you actually have a native USD already built to go faster, which I'll explain. And we were also sourcing shot grid data to get frame range, to get cut range, etc. And overscan or anything we could. Yeah. So just to explain at the time, so we had like this kind of asset importer. You get a bunch of shots. You know, it was really great and fast to actually get everything we need. As a matter of fact, Matt was here, actually made that. And so, yeah, you know, it was like, you do a little right click, you say, I want whatever is needed for my shots, and you would pull everything you need. And it was great. You know, you start from zero and you have this, it was great. Sure, after thousands of assets, it was getting slow. But you learn over the time, right? So that's like a typical node graph that we would have. And so you can see that from the top to the bottom, it's quite a few things. Doesn't seem like a lot, but that's also because on those shots, we had like one set, 2 characters, a very few props and 3 types of cameras. So it doesn't get too big, but it shows still that it is a certain amount of management to do. So this in this example, so we were bringing our shotgun data, we had our set, we were bringing USD override. So the USD layering was another part that we would apply to the assets. And then we would do this on a bunch of assets. That would be, for example, in this shot, you want this object to be moved there. In this shot, we move there. So naturally, we would only export the minimum information to do that. Render camera, you see multiple types just because we have real-time match move, multiple type of camera. It's not very interesting. And so in this case here, we had our look dev. So in this case, you see Kurama. This is from Yu Yu Hakusho. I don't know if anybody saw it, but so anyway, Kurama is one of the characters. And it's funny. The arrow and the text moved. I'm very sorry about this. So that HDA that I just mentioned here was what we used to deform things. So basically, we would export Alembic from animation. We would use this on the look dev and just simply get the asset deformed. And that way, we would always be able to, you know, have that look dev applied to whatever animation we do. We were actually doing this for grooming as well on Oni. So it was very nice because we never cached anything. So it sounds nice on one side and it sounds very heavy on the other side. But on Oni, there's just no way we could afford doing so much storage. So we were deforming things. Then you can see we were disabling or enabling groom character just to try to optimize things. And then in this case, you can see the content of one of these red nodes, which is basically just like whatever USD comes from a bunch of shots, and then a switch that would, you know, you would just simply say, I want to be in that shot. Everything would switch to that shot. And within one scene, you would manage 80 shots. Like we definitely had some sequence on Oni that were 80 or 90 shots. So very convenient. But I'm going to add another adjective to that after. So, you know, even though it was heavy and it was like not necessarily the most optimized way to work with it, we pulled that off. And honestly, with maybe at the most, we had like 5 lighters. And we had a really small team on Oni. So pulling off 2,200 shots with this, and I've been working on this for a while. I've been doing series like almost 20 years ago. I can tell you, without Solaris, we would have not even done that show. So that was a big, big deal. Now let's switch to what's next. So just explain, we did a few other projects since then. So it's not like just only, we use the exact same workflow on the live action show. No difference whatsoever. We actually had like about 400, 500 shots of CG on the zombie 100 stuff. The other one are a bit smaller, but this actually also 500 shot, but yeah. Anyway, now learning from that iteration, that's the important part. So the scene assembly in a lighting file is bad for multiple reasons. It's inefficient and slow. Sorry, I got a bit broken here. Prone to error. I might not have time to go into detail too much, but for instance, when animation would maybe put multiple times the same instance of the character, the only way you have is saying box 001, box 002. And then the days they decide that, oh, we want to make this box, but we don't want to destroy this animation, so they're going to create box 3. Then box 2 is useless, and you have box 1 and 3. But then the lighter have no idea. Like, it's coming to them, and they're like, oh, why it's now broken? And we didn't have a way to catch this in this current situation. Additionally, it's very easy when you have this kind of graph to just go and yourself do some manipulation. And then after that, completely forget that they are here because it's pretty big. You just put some customization here and there. Even though there is a rule, don't touch what's above the assets, there is time where you're like, well, I need to work, I need to go. So, it's easy to understand. But because of that, there's few things that we felt like are not stable enough. We need to find how to make it easier and how the lighters can receive something that does not have to be fixed. Then, oops, sorry. Let me, it's fine. Creates a large amount of nodes and make the file hard to read. So I explained earlier, it's quite heavy. So naturally, after a while, when you get on this 90 shot sequence, you save multiple times and you feel like, oh, I should have split that sequence. Yes, and whatever you do is not necessarily spreading to other sequences or, yeah, anyway. So, oops. Fixing data in the lighting scene is not ideal. Houdini makes it easy. So that's what I explained earlier. I'm sorry, I went ahead, but fixing things is very easy in a node, but it's not ideal for a workflow. USD in general should not be used just for look dev. And we should make sure that everything we have is inside the USD. Scene assembly should be clearly defined, and that should not happen in lighting file. I don't think I have to say more about that. Now, just to very briefly illustrate it, this is like the simplest example where you can see, I'm going to use the mouse. We have our asset created on database, shot grid, flow, whatever it is. Create asset folder. And then from that, we start working. We have a modeling, a groom, look dev. So you export some geometry, you export some textures, you gather them all, and then we put everything in a USD. This is what we were doing at that time. And nothing wrong about it, but not necessarily the most efficient way to work. Now, what we decide to do from here is rework the asset primitive structure to match any kind of like convention, any kind of standards that we can find. Obviously, in a few years now, so many people are using it, so many people are sharing how they are using it. And the most importantly, many people have the exact same experience as us, thinking, oh, what's the most efficient way to work with it? Improving the asset composition, creating some base structure by classes, in classes. So, oops, sorry. This gets a little technical. I'm not going to expand too much on that. Making more refined usage of purpose and variance. I mean, as you know, USD is pretty powerful to do a lot of, it's not like you have an asset and you just have a model, right? You can actually, within an asset, you have control over any kind of level of details. You can have multiple textures. You can have so many things inside your USD that you can control. And for example, lately we've done a project. We have a big thing happening in Tokyo, and we wanted layout to be able to work with a realistic city, but obviously not too heavy. So, automatically processing every single building to get this very, very simple version of broken buildings. So at least you still get the right silhouettes, but it's very light for them to manipulate. This is the kind of stuff that the LOD use, and variants allow you to work with. And then now we actually cache USDs because it seems to be working generally in other software. Cool. So our latest iteration also has complete USD structure for project sequence shots. So I kind of want to take a shortcut and mention that basically now I'm describing a USD as pretty much your database on the disk, right? Not just for your shot data and stuff, but like being your plates, being your information for the shot, being in the audio, everything can be contained in your USD. And so what we do now is actually to be able to simply copy paste one shot to someone else. That's what we do. We improve the description of our USD and we try to get all of that in there. So, to really simplify the flow. We're not yet there to have absolutely everything, but this is exactly where we are going. Clear scene assembly defined by a manifest. I'm going to show the manifest after what it is. As I mentioned, using USD to store data that were on ShotGrid before, representing media type like plates and audio. We use payloads a lot more. We were not at the beginning, so everything was loading by default, which was not necessarily the best approach. And then, as I say, we stop ABC. So this is a little closer to what we do now. So you can see that before, when we were exporting this into a USD, now instead, we define our USD to start with. We have this description of our USD here, which, sorry, it's maybe a little small to understand, but it's very pretty much a container. Just to say, okay, in my USD, I'm expecting to potentially receive geometry, model, geometry, textures, anything really that can come there, proxy, groom, etc. And then each department is going to do their work. They're going to export their own layer, and that layer will be added to this layer. And it's what USD is for. It's to be able to work that way. Just that it takes time to actually implement that structure. And now we are there a lot better than we used to be. And this is for a shot. It's pretty much the same thing. But, just more layers. And I didn't write here what the shot frame range and all that stuff that we are adding. But yeah, this is the manifest. So what we call the manifest is basically, it's very simple. It's the description of our shot. And what we do in that is instead of letting layouts just dropping things in the scene and publishing them, instead of just having ShotGrid or any software, production software, listing the assets we need, we went to something where we developed it ourselves and we have so much more control. For example, we can control exactly the amount of instances we have. So that means when they get published, if the animators made these extra instances, it's being caught and it's like, I don't understand why you're trying to export roulette 3. I'm expecting to only have 1 and 2. Animators fix their stuff, lighters receive what they're supposed to receive, and everything is much smoother. We have, the ability to say, okay, for this project, I want this geometry to always be in there. For this sequence, I want this set to always be in there. And for these shots, I want this and that. And this is all coming from ShotGrid, in our case. So shots and assets. Then the middle is the contents of the USD of the shot. Just an example is, we can actually mention, okay, I want this LOD, I want this variant, etc., for every single asset. Going back to what we had originally, our multi-shot workflow, now it's a lot simpler because within that, you actually have the entire graph you were seeing earlier. And the shot is basically all here. And now I feel bad. It's a little small. I'm sorry. So what you see here is, so basically you can pick whatever shot you want to load. From here, you can switch to whichever shot you want to see. And all of here is very important, is you can actually load and unload any single layers of the shot. So you can see your shot only the layout layer, then you can add to it each layer. And that allows you actually to debug so much faster and find out where the problems are coming from. And same for QC as well. It's really simple to set QC of this type, this type, this type. So yeah, on daily basis, so if I go back to the usage of Houdini, what we like here is that you have really high level of access to anything. I mean, basically, we can do anything we want, from the simplest code to any complex tool. It's in the case of Solaris, honestly, without doing a prototype in there, it's very difficult to actually build what we've been building. So it's kind of great that we have pretty much every kind of access and control through it. There's a lot of code that already in there that is extremely useful. When you dig in Solaris, there's already a lot of tools that exist, and it's very, very nice when you want to make your own to find out, because that is not very well documented online, any kind of USD code. Obviously, HDAs are very useful to users. And speaking about this, I'm going to introduce Andrew Palmer and Matthew Puchala. Andrew is going to talk a little bit about some tool we are using every day that is kind of making our life very easier, and showing a little bit of like how powerful HDA can be. And Matt will talk a little bit more about some fluid solver we decided to add to our plugins. That's it for me. And I'm going to leave it to Andrew now. Here you go, Andrew. Oops. Wait a second. Here you go. Cool. You should be able to play these things and just press here. Okay. Each time you want to do the next one. Okay.
Okay. Thanks, Chris. Hi, so I'll introduce myself. My name's Andrew Palmer. I'm the lighting and look dev supervisor for Megalis VFX. And something we thought would be kind of cool is just to show you a template system that we built for Houdini, and a tool that we use for look dev every day, just for setting up turntables really quick, and how that sort of integrates into our USD workflow. So I've got a couple of screen recordings, and I'll just go through them and kind of talk over the top. So so this is a custom template loader, and it's pretty cool for a couple of reasons. It's very artist friendly in that it's very visual, so there's no like hunting for data or anything like that. The way we've separated it is into sort of department and then Houdini like context level. So we can see like in the TD context, we have like object level templates and SOP level templates. In the look dev department, we have this one called TT Mega. It's sort of like a all-in-one look dev rendering template. We can also see that the templates capture the full res environment. So if we ever need to roll back to something, we've got all that information handy. Yeah, and this is it's kind of like a HDA, but contained within our template, but it's all in Solaris. And what's really cool with Solaris gives us the ability to react on assets really, really quickly. So I'll run through the next video. Cool. Cool. So we can see up the top, we can set a department because this tool is used across multiple departments. We can see our project and our asset. In this case, it's the Pixar teapot or shark pot. And we have a couple of predefined light rigs. So this one is our base physical studio, which we pretty much render everything in with assets borrowed from the Pixar studio. This is mainly used for larger assets like vehicles, cars, that sort of thing. This is our portrait rig. This is our texture XYZ rig that we use for skin, sunny outdoor environment, and an overcast environment. So we also have a couple of controls here as well. We have this fast viewport control, which does exactly what it says on the tin. It keeps the viewport fast by bypassing a bunch of like render-man AOVs and that sort of stuff, because the render-man AOVs tend to slow down the viewport. The more things you kind of cram in there, it starts to slow down. So added a quick toggle so that we can keep the viewport nice and snappy. A byproduct of that is it actually disables the interactive denoiser because you need AOVs for the denoising to work. That's a little bit of a trade-off there. We can also add a ground card for shadow catching and stuff like that. But you can see just by plugging the asset in, we have an automatic camera system which works based off the bounds of the asset. So you can just drop this node in and it basically auto fits itself. We have some very simple controls just to help frame things. And then we have our animation controls. So again, this is targeting like USD primitive types, as you can see, like type boundable. So any geometry that's going to come in, regardless of whether it's a published asset or like just a sublayer like this one, it's going to catch it and frame it and do the right thing. And then same deal with the lighting. It'll target any light types and things like that, which is pretty cool. We have a couple of different modes, so we can rotate just the asset or rotate just the lighting, and we can apply offsets very quickly and that sort of thing. And like so. And then under our rendering tab, so we have a list of render delegates. So we're using RenderMan RAS primarily, but we are sort of starting to use XPU a bit more now that since RenderMan 26, things have gotten a lot more stable. So yeah, it's pretty cool. So we're making sure that, you know, we're enabling access to that. We have a couple of settings, low, medium, and high, to just help the inform the artist more than anything what those settings should be. Frame range, things like that. Now this part's pretty cool. So this kind of ties back into our USD workflow, where the output names of our renders are all procedurally generated, and this is gathered from the USD information within the scene. You can kind of see down here, as Chris mentioned, we have classes. What this tool will do is that it climbs up the scene graph and finds the incoming assets like geometry and material variants. So if we're looking at different variants, all of those outputs are just set automatically. So again, it's just another thing that the team doesn't have to think about, because output names is not what they should be focused on. It should be, you know, doing the work. But yeah, that's a pretty cool feature. And touching on that, we can see these are our dynamically generated output paths. So they contain things like the light rig, the asset, the variant name, that kind of stuff. So again, it's just empowering the artist to focus on creative and not naming and output locations and all that stuff that's kind of people don't care too much about. So let's just show a version of this in action. Whoops, sorry, jumping ahead a little bit. Where is it? Cool. Okay, so cool. So this is basically from start to finish of how like a look dev artist would typically set up an asset and just how fast it is. And you'll notice once we actually start rendering, something we really like about doing look dev in Houdini and RenderMan is the Hydra viewer is shockingly agile. So you'll see like once the renderer starts, we can change the scene graph like quite dramatically, and we don't need to restart the renders at all, which you'll see in just a moment. So kind of setting it up, checking that the model is valid, and then we go, yep, okay, cool. Let's start rendering something. There's our shark pot. So this asset has a material variant. So we have like a default variant and a green variant. Without even stopping the render, we can change all this. We can move the lights around, to get a really fluid preview of what we're working on. We can turn the fast viewport off and initiate the interactive denoiser, which actually does change the scene state, as I mentioned before, because we're adding AOVs and stuff like that. Yeah, it's pretty for look dev work. It's pretty awesome. It's very fast and interactive, as you can see. Yeah, going through all these scene state changes, still haven't disabled the Hydra viewer. That's pretty cool. So so I'll finish off and hand you over to Matt just by showing you some actual renders produced from our environments. So that's our shark pot rendered in our studio, 100% through Solaris and USD. We have another teapot provided by RenderMan, but we also don't just render teapots. There's some CFX testing that we'd love to show you, but maybe next year. And then all RenderMan as well. So cool, that's it from me. I'll hand you over to Matt. Cool, thank you.
Okay, good to go. Cool. So I'm Matt. I'm a visual effects artist. I'm also the developer of a fluid slower plugin called Axiom for Houdini. And today I want to talk a little bit about just, what Axiom is, just kind of in general, what kind of makes it special, then talk a little bit about the integration inside of Houdini, and then finally show kind of like a use case of how it was used at Megalis on a project. So let's go ahead and just kind of break it down line by line here. So sparse What does that mean? So kind of back in the olden days, we would simulate kind of like this. This is what we call a dense simulation, meaning that the voxel grid is kind of arranged in a very kind of regular manner. Everything inside the red box is what we call the domain, and it's contained voxels, and we basically compute everything here. Even the areas that aren't necessarily interesting, don't have white smoke, all that like empty black area, we're still simulating all of that. And this is fine. However, it obviously uses a lot of memory to still fill up those empty spaces, and we need to waste computation time and resources to simulate all that empty region. So now we have a new technology called sparse grids that look a little bit like this. So basically, to get around the fact that there's lots of empty space that we're computing, instead we kind of break up the simulation to millions or thousands of little what we call tiles that are just groups and collections of voxels. And we're basically just putting those wherever the interesting bits are. In this case, we only care about really the white smoke here and the trails. So we're only going to, allocate memory for voxels in those locations, and we're only going to compute those regions. And the benefit to that is you can see over on the dense simulation side, this simulation, it might be overkill having a resolution of this high for such a very simple simulation, but it was 1 billion voxels and it took 78 gigabytes of memory versus the exact same thing with sparsity. We have 64 million voxels and only used around 5 gigabytes of memory. And, it simulated an order of magnitude faster than the dense simulation. And, if you're not optimizing your output volumes as well, it's obviously going to take, a lot more memory on space as well if you're not like pruning voxels. Then we have GPU accelerated, which very simply means it runs on one of these. It does not run on one of those, unless you're using OpenCL, which can actually utilize, the API can be run on many, many various different kind of devices. And Axiom is designed to run on these 3 compute APIs. These are all different frameworks that allow me and other developers to, and like game engine developers and just, high performance compute developers to put code and write code that can run on, GPU hardware. And these all run on various different hardware. Obviously, NVIDIA is going to run only on, NVIDIA CUDA is only going to run on NVIDIA hardware. Metal, which is the Mac OS kind of compute and graphics framework, only going to run on, Mac devices. And then OpenCL kind of covers everything else. So if you, for example, are running on AMD, you might use OpenCL as kind of like backup. And I like to say, choose the API that, matches the vendor if possible. You're probably going to have the best support, usually depending on how the drivers are going these days. But yeah, it basically covers across many, many different kind of hardwares, and it's supported on different kind of hardwares. So then, getting Axiom and the sparse simulation grid to run on a GPU was a bit tricky at first of a problem to figure out. GPUs like very regular data. Like here is what we call basically a dense simulation grid. And, it's a row in columns of very evenly spaced voxels, and GPUs like this. Because, at the end of the day, GPUs were designed to work on, creating 2D images, which are just basically 2D grids of voxels, or pixels, as we call them. So GPUs like this makes a lot of sense to them. They're kind of designed to work like this. Then you try to get the GPU to look at an image like this, and it's like, okay, this is very complicated. I don't know how to kind of deal with this. So that's kind of the trick of Axiom, is how to kind of get this complex data structure to be understood in the GPU in a way that doesn't have too much overhead. And the way I kind of got around that was by taking this very complex data structure and effectively just lining up all the tiles in a one big row. So what the GPU, as far as it's concerned, is it's one really, really, really long 3D voxel grid. And that's kind of the representation that the GPU is concerned about. And then I also feed it just a little bit of information about okay, every 16th voxel is a separate tile that has its own position in 3D space, its own size potentially. And that way I can start to do, relationships between voxels for doing blur operations or something along those lines, and start to get these tiles to communicate between each other while, having the GPU have it in a format that it's very, happy to work on. Then volumetric fluid very simply just means it does gaseous type simulations. It does not do liquid type simulations. They're both technically fluids, but in CG, we like to take separate approaches in those. More of a particle approach for liquids versus a voxel-more approach for, gaseous type effects. And Axiom is a volumetric kind of gaseous fluid solver. And what that kind of boils down to is that you can create simulations like this. So this is a few kind of test simulations I did while I was developing Axiom, kind of like the early days. We've got a nice little explosion in a tower here, and we've got a nice little half of a volcano exploding kind of simulation here. And this shot I actually, I worked on when I got a loaner unit from Apple, and they basically told me to try to push the new M1 Max machine as far as possible. And yeah, I like used the maximum amount of RAM as possible to kind of push this. And I think it was like around a 1 billion voxel simulation that finished on my MacBook here, the same one I'm presenting on here, finished in I think like 40 minutes or something like that for 1 billion voxels at the end of the day. So it's absolutely incredible how performant it is. And then, of course, I've been using Houdini since I was like in high school, I think, well over 10 years, I think, at this point. So, of course, I'm going to be integrating it into the app I love. So I've, of course, designed it around a very like Houdini-centric workflow. So Axioms, all the tools are available to you in SOPs. You have, of course, the main solver node, but also a few extra utility nodes, similar to Labs tools. They just kind of build off of the, really good, solid foundational tools that we have in Houdini, but just kind of build on top of them to make it easier in like different Axiom workflows. And I love Houdini so much that I don't actually want to leave the app when I'm doing performance profiling. So I actually built my own performance profiler as a Python panel in Houdini so I can debug shaders, find bottlenecks, figure out like timing and performance and everything like that, memory usage, you name it, it's all there. It's actually available to users. You can actually, load up the Python panel and debug your own simulations as well. But yeah, I didn't want to leave Houdini, so I made a profiler for Houdini. And of course, it was very important that Axiom work with all of the rest of the really great tools that are available in Houdini. So I'm happy to say that Axiom works with pretty much all of the really great sourcing presets and kind of like templates that exist for Pyro. So you can take one of the Pyro kind of like emitter presets, drop Axiom in, and it will work no problem because Axiom's designed to understand all the naming conventions that, Houdini users are used to creating and working with. And that, the developers at SideFX have, chosen as default. So I made sure that Axiom can understand all of this different naming convention. And in turn, Axiom outputs very familiar just VDBs with the exact same naming convention that, later down the line, different Houdini tools can use and also can be understood by like Karma or some other render engine. And because of that, you can very simply take like a quick fireball that you make, drop into like a Labs flipbook texture, and actually like within minutes, you can have Axiom simulation rendered as a flipbook and running in Unreal, all like literally in a matter of minutes. I think I got this working in like under an hour or something like that from simulation to what you see here. And then kind of building on top of that, in the latest version of Axiom, all my users have kind of been requesting that I support height fields, and height fields are great because they're much easier to sample than converting like giant terrain into a VDB SDF and then sampling that. It's much easier just to sample a 2D image instead of representing height. So now Axiom can support height fields directly, just like any other source. You can plug it in there and it will understand it no problem. And Axiom also has one extra little trick up its sleeve, and it's what I call source shapes. They're basically just mathematically defined shapes that you can use for sourcing, for sinks, for pumps, for collisions. You can use it for camera frustum as well to call anything outside the view or that's really, really far away. And if you don't need something that's super, complicated or detailed as far as a emitter is concerned, you can just drop down one of these source shapes and it'll be much faster than, converting a sphere to an SDF and sampling that instead. And of course, I try to make Axiom work for the majority of use cases that you might need a fluid simulation for. So it has all the different simulation kind of controls you expect: buoyancy, dissipation, diffusion, wind, disturbance, turbulence, confinement, a full combustion model, you name it. I like to say that Axiom can cover 90-95% of all the different like effects that a typical artist might want to work on in a typical shot. And so quickly, I want to show you just how easy it is to work with Axiom. So here is me creating that fireball simulation that you saw in the Unreal demo. And I'm creating it in I think this is a minute, 15 seconds. So I'm just dropping a source shape, dropped on the source. Then I'm going to link up all the parameters so that I can animate them all together and don't have to animate all the parameters separately. I'm going to go ahead and just drop down some keyframes. That lets me get a quick blast at the very beginning of the timeline. And then I'm going to go ahead and just, ramp it down and set another keyframe. In the solver, I'm going to go ahead, drop fuel a little bit so we don't get so much of an explosive force. I'm going to enable combustion so we get that nice pressure release at the beginning. I'm going to enable disturbance for the higher frequency detail, increase turbulence to make it more swirly. And we have a very quick, nice little fireball. And this is all in real time. Nothing here is sped up. This is running on my MacBook here. And now I'm going to drop down a Pyro bake volume so I can take advantage of the really nice Pyro shader, crank the density up, make the smoke nice and black so it's crunchy. enable scattering, just set a more appropriate range for the kind of hot areas, adjust the mask a little bit, and you have a nice little fireball, all in about 1 minute and 15 seconds. You're ready to go. You can drop it down your lab's texture node, bake it out, and you basically have a game-ready asset in like 1 minute, 15 seconds. So it's a really, really nice, easy way to work, I think, all with just 3 nodes very quickly. So then at the very end, I just want to talk briefly about Megalis. So at Megalis, I'm very proud of the fact that they use Axiom a lot in all their projects. They recently used it on their show, Yu Yu Hakusho. So I'm just going to show you a few examples of what they did. And for this show, it had a lot of different kind of pyrotechnic effects in a very large number of shots that had to be completed on a very tight deadline. And, you know, just because Axiom is just so fast and efficient and it can, you know, allow artists to iterate very quickly, they can get new versions out in a matter of minutes instead of hours. So it's a really, really nice way to work. So yeah, that is my presentation. Thank you very much. And I very quickly just want to say also, you know, just thank you everyone for coming, and thank you to SideFX for your continued support in my development efforts of Axiom. Definitely appreciate it. So again, thank you everyone for your time.
Boom! That was awesome.
Thank you.
Nice work, the 3 of you. Any questions for these guys? I'll give you a second. Okay.
2 questions about Axiom. First, have you considered replacing OpenCL with Vulkan? And second, can you get access to GPU buffers of the simulation after the simulation?
I'm sorry, could you please repeat the first question?
Have you considered replacing OpenCL with Vulkan?
Yes, just because it feels like the more modern version of it, but I just haven't gotten around to it. It could be very cool if SideFX were to, you know, allow developers to directly take advantage of, you know, the Vulkan buffers and the new Vulkan viewport, so I can, you know, render directly. So, you know, I would very much like to do that for sure in the future. And what second question? Sorry.
Yeah, and the second question, can we get access to the GPU buffers so we don't need to read back the simulation back to the CPU to process it?
I wish I could say yes, but not at the moment. I would very much like to know what kind of, how you imagine that workflow, actually. We can talk later, but yeah. Yeah.
Sounds like you have a follow-up discussion. Any other questions? Going once, going twice. Awesome, guys. Very good presentation. Thank you very much.
Thank you.